Bismillahirrahmanirrahim. The marine equation that we have studied in the previous lecture, it catered for different factors: surface finish, size, loading, temperature, reliability. But one thing it didn't include was any uh, talk of stress concentration. So, stress concentration factor wasn't even considered when we use the marine equation to get SE from SE prime. Now, why is this important? All sorts of mechanical components, they have notches or grooves or fillets, section changes, holes, keyways, etc. These are all design features. So you cannot avoid these in most components. Now, if you have these features in any component, then obviously stress concentration factor would play a part, because you have considered all those things that could affect the performance of a material or of a component in actual use. Then surely these must also be included. Now, stress concentration factor in itself, it's a familiar concept. You've already dealt with these. And just as a recap of what we do know about stress concentration factor, uh, let's consider this. First of all, it is if you are dealing with brittle materials. What is the stress concentration factor when it comes to brittle materials? It's called the geometric stress concentration factor, or the theoretical stress concentration factor, and it is called KT. T is for theoretical. Now, it's also called geometric because it only depends on this. It has nothing to do with the material you are using. And this is the KT that you read off the charts, of the different charts, depending on the type of loading and the change of section dimensions, etc. But now we are not dealing with brittle materials in this course. We are not focusing on these, at least in this course. But if we have to design brittle materials, then this KT is the thing that we need to consider. Now let's take the next kind of material, or the kind of situation that you may encounter. That is ductile materials failing in a ductile manner under static loading. You are using a ductile material, and this is surely the focus of this course, and you apply some load, static load, constant load, or monotonically increasing load, and the material fails, and it fails in a ductile manner. It pretty much like a tensile test. Now, in these cases, if you recall the yield criteria, because here we are surely talking about yielding. So if you recall the yield, when we studied yield criteria, we had said that for these situations, ductile materials and failing in a ductile manner under static loading, very specific conditions, you can take the stress concentration factor to be 1. And why is that so? That is so because, let's say this is a very familiar example, plate with a hole. You apply loading like this, and obviously there's a stress concentration here, but the stress, it could be very high. The nominal stress obviously keeps on increasing, and then you multiply this with the theoretical stress concentration factor, which is actually not 1, it is actually, maybe it is 3 for this whole situation, but for other kinds of discontinuities it could be even higher. So you have this kind of a stress distribution. Now here what happens actually for ductile materials is the stress doesn't rise as high as the theoretical stress concentration factor would suggest it should rise. And what happens is, because it's a ductile material, it yields here, and obviously when something yields, then there's a limit applied to how high the stress can increase. Even if you consider the strain hardening, there's a limit applied here. So what happens if this yields, you keep on applying the load, then the next section yields, and so on. So what happens is something like this, gradually, and then the whole section yields. So here the effects of stress concentration at this point were mitigated by the yielding of this section, and then that yielding increases in area, and until the time when the whole section yields, and this stage is called general yielding. So if this was a brittle material, there would have been no concept of yielding at this point, so the stress would have been very high at this point. So, but we are not dealing with brittle materials here. So in this kind of a situation, you just take the KT is equal to 1, because in any case it will yield here and then the yield will spread. It isn't that the stress will become very high here and it will break or something like that. So in that case you are justified in using KT is equal to 1. So this was the second case. We are still discussing stress concentration factors. Now the third case, ductile materials. Fracturing in a brittle manner. Mind you, this will also, when general yielding takes place and then you keep on pulling it still, then there will be some sort of quite a lot of plastic deformation here and some sort of necking and also that sort of thing, and then post strain hardening, ultimately it will break also. This will also break, but that breakage is called a ductile fracture or ductile failure. What we are discussing in the third case is ductile material fracturing in a brittle manner, again under static loading. And if you recall, now I'm talking about this sort of a situation. We extensively dealt with these situations when there's a crack. This crack is very different from a design feature like hole, because there's a finite radius here. Here the radius at the tip of the crack, theoretically speaking, is 0. So there should be infinite stress. Obviously, if you recall, there is very high stress concentration here, but we dealt with this kind of a case using the principles of fracture mechanics. And what we did was, we didn't bother. Here we took KT is equal to 1. Here we didn't even bother about the stress concentration factors. Stress concentration is there, but if you recall, we found the nominal stresses at sections away from this, and then here we found out the stress intensity factor to characterize the severity of this, and we made sure that this K1 was less than the K1C, the fracture toughness of the material. So this is the third case. So we are dealing with the same stress concentration factor, but for brittle materials we use KT, although we are not focusing on these materials here. For ductile materials, failing in a ductile manner under static loading, we take kt is equal to 1. No harm in that, and there's no contradiction here either. Now we come to the third case, ductile materials fracturing in a brittle manner. Then this is usually the case when there are cracks there and the crack is nearing or it is equal to the critical crack length. This is what happens then, and for that we don't even bother about the stress concentration factor because we use the stress intensity factor K1. Because stress concentration factor has to deal with, it always deals with the situation where you have finite radii. If the radius is 0, then theoretically speaking it is, the stress is undefined or infinite. So we have obviously successfully dealt with using stress intensity factor instead. Now we come to the fourth case, and the fourth case is what is the topic today. It is ductile materials failing in a brittle manner as a result of fatigue loading. This was also brittle, but this is something else. The loading is not monotonic, it is not static, it is changing. It is tension, compression, or different levels of tension. Now in this case, still the failure is a brittle failure. The material is ductile, the failure is brittle, but the difference here being that although the material is ductile, but there is some level of local yielding still takes place, because remember the material is ductile. So although it fails in a brittle manner, but not before some sort of local yielding takes place. And what we are talking about here is, again, this deals with actually the initiation of cracks and then the progression of cracks. But at each step, small amount for the progression of cracks, small amount of local deformation, plastic deformation or yielding, it still takes place. So although it's a brittle failure, but you cannot rule the local level yielding completely. So you can say that ductility is there in some degree. That's what's different between this one and this one. Here, if certain conditions are reached, then after that it just runs away. Here the stress, the crack first initiates and then it increases in length, and at each stage, even if it grows, some ductility is there in the material. So what happens here is you cannot completely deal with it in a brittle like a material which is completely brittle, although the failure on the whole is a brittle failure, but some ductility is there. Now how much ductility is there? That is an interesting question. Some ductility is there, but how much? Well, it depends on how much the material yields. It's actually the same thing, and that is actually, it's the same thing basically, and that depends on the material. There are materials which are easy to yield, and there are other materials which are less prone to yielding, and then the severity of the discontinuity, and we'll discuss this in detail a little later. Now these two things, both of these are characterized by what is called the notch sensitivity. So every situation, and the situation means the material as well as the size of the discontinuity or the characteristics of the discontinuity. Both of these play a role, and each situation containing these two is characterized by this thing called notch sensitivity Q. Now we'll discuss Q, but how this Q depends, how this Q affects this case. This our fatigue stress concentration factor. In this case, we use, in the fourth case, we are not going to use the theoretical stress concentration factor, but we are going to use the fatigue stress concentration factor. Now, how the Q affects Kf is in a very simple relation. Now here, this is the theoretical stress concentration factor, and this one is the fatigue stress concentration factor. So in all these situations where we are dealing with fluctuating loads, we'll be using Kf instead of Kt. Now, what does this Q mean? Q, the two limiting conditions, Q is equal to 0. It means the situation or the material is not sensitive to the notch, and by notch I mean all the holes and the section changes and everything at all. So it's a theoretical case. There's no such situation where a material is not sensitive to notch at all. So this is just a theoretical situation. But in this case, Kf, if this becomes 0, Kf becomes 1. So under fluctuating loads, there is no situation where you'll have this situation. What is the other extreme situation? Q is equal to 1. It means the notch is, the material is fully sensitive to the notch. Now in this case, if you take this Q to be 1, then it's very easy to see that Kf becomes Kt. Now this also never happens for a ductile material. For a ductile material, this never happens. So what actually happens is, the value of Q, it lies between typically 0.7 to 0.9. This is the actual range of the ductile materials, those which we use for design usually. So you can say that if you put these values here, you can say that Kf is somewhat smaller than Kt. So in other words, the effect of stress concentration is somewhat reduced because of local yielding. Somewhat reduced because of local yielding. Now we'll discuss this Q a little more, but first of all, where do we find Q? Well, in your textbook, there's this figure 620 and there's the figure 621. Here you can read Q for normal stress situations, and here Q for shear stress. It's very easy to read. We'll discuss some more about this Q, but where do you find this Q? It's easy to read of a chart, of a figure. Now let's discuss this figure 621, and I'll just discuss figure 620, and the same discussion holds for 621 too. So this is figure 620, and it's easy to discuss the effect of the material as well as the severity of the crack on Q. Now here this is not sensitivity Q, and this is one fully this is fully sensitive, and this is not sensitive at all. And here you're talking about the range where you usually get your values for real materials. On the y-axis, on the x-axis you have increasing R. We are talking about radius. For example, change of section, this is R. In case of hole, this is R. So in any situation, whatever fillet or radius is there, this is R. So what happens is, for example, this is 0, this is 0.5, this is 1, 1.5, and so on, and there you have 4 millimeters, for example. Now here you have lines. For example, this line is for steel with ultimate tensile strength of 1400 MPa. This line SUT of, let's say, 400 MPa. So now it's easy to discuss this. As you get the materials with higher yield strengths, for example, the higher yield strength means these are the softer steels, these ones, more ductility here. So you have less notch sensitivity, as should be the case. And the so-called harder materials, and I don't use the word hard in the technical sense, the materials with higher tensile strengths, these are generally less tough as compared to these ones. So here you have less likelihood of ductility, although they are also ductile, but these are more ductile. So as you go up on this scale, these are the stronger materials. Here you get more notch sensitivity. Here you have less notch sensitivity. Now what about radius? If the radii are bigger, if this, for example, this hole is a big one, then the stress concentration is less. Stress concentration is less, so the stresses are less. If the stresses here are less, then there is less chance of yielding. On the other hand, if the radii are smaller, then you have higher stress concentrations. Higher stress concentrations mean higher levels of stress, and higher levels of stress mean bigger yielding. So the notch sensitivity decreases as you come to lower R's. Now this can be misleading in some cases. For example, it's very easy to think that if that is the case, then R should be lower, so that we have higher notch sensitivity, we have lower notch sensitivity. But the thing is, if you decrease the R for lower R's, we have lower Q. That's all right. It's good. But the thing is, for lower R's, we have much higher KTs. So if you recall this, if you want to have this smaller, obviously you need this to be smaller. But if making this smaller means that this becomes very high, then the net effect will be KF will be higher. Only KF will not be as high as KT would become. Q will slightly temper it, but not completely. So you have to keep this in mind, that it's a good thing that for low values of R's we have lower notch sensitivity. It's a good thing, but at the same time we have very high values of KT, so the net effect of KF is to increase. So it still is a good idea. So the first, obviously, if we talk about this one, it's still a good idea to use bigger R's. And the second lesson from this chart is it's a good idea, and it's a very obvious one, to use tougher materials. And this also is a very obvious one. So maybe this one is slightly difficult to understand, but this is very obvious. So the summary of the story is, if you have a fluctuating stress situation, and this is what we are talking about here, then for lower R's, KT will become very high, but Q will become low, not in the proportion of KT, but still somewhat low. So the net effect will be, so Q with R, KT increases tremendously, Q decreases, but not in the same proportion as this one. So the net effect is KF increases, but not in the proportion of KT. And it's a very good thing in nature, because we have situations where we have very small R's. So for small R's, KT increases, that's inevitable. But the good thing is that KT increases but Q decreases, and therefore the KF, which increases but does not increase as much as KT. So there's slightly some mitigating of the stress concentration. So we'll be using this KF, and which will always be less than KT for these situations. So this is as far as the talk about KF, or stress concentration factor for fatigue, is concerned. Now I'll just finish with one point which sometimes causes a problem, which it shouldn't, but still, just to make sure it doesn't. KF is always, or you should always, should always be used to increase stress, not to decrease strength. What did we use to decrease the strength? If you recall the Marine factors, they were all applied on, you had this SE, and here you had SE, and you had all these factors, they were multiplied to this is endurance limit, which is a strength parameter. You applied all these to decrease this, to get this. Now KF can also be, theoretically speaking, you could add here SE is equal to all these factors that you have all considered, and you can take 1 over KF. You can decrease the strength also, theoretically speaking, but you should never do it. Why? You should always keep this as, you just use the Marine equation to reduce the strength or whatever, to modify the strength, and you should use KF for the stress parameter. For example, it's a axial loading case, you should use this. If it's a bending case, you should use, and so on. Why? Because if you have a case of combined loading, then you have different KFs for the same geometry. You have the same geometry, but the loading is different. Axial loading, and for bending you'll have different KF because KTs are different. So how can you reduce the strength when you have different KFs? When you have combined loading, there is no other option but to apply the loading, the stress concentration factor to the loading, individual loading. For axial loading, you'll apply it here. This one will be different from this KF. You apply it here for bending, and there's a torsion. If there's a torsion, you apply it there. And what to do when there's a combined loading case, we'll discuss later on. But for now, you must always remember that if you apply KF to increase stress, this will work in all situations for simple loading as well as combined loading. But if you use this KF to reduce strength, you can also only do that for simple loading cases. For combined loading, this cannot work. So the good practice is to always use KF to decrease strength. Uh, Now we are ready with the knowledge of marine factors as well as the fatigue stress consuming factor. We are now ready to tackle some design and analysis problems. Thank you.